All right, guys. Hey, welcome back to another lesson. Today we're going to talk about polynomial functions. This will be like a two-part lesson. Actually, the second part's a different lesson, but the lesson after this is going to continue the conversations that we have in this one, okay? And we're going to talk about polynomial functions, okay? And specifically, we're going to talk about analyzing their graphs and what their graphs mean with the equations and kind of just make some connections, okay? So let's just jump right into it. First things first, what is a polynomial function? Which I'm glad you asked. Okay? A polynomial function is a continuous function, and this is important. It has to be continuous. There's no breaks. Okay? So I have some sort of function that just continues going on forever, like this. Okay? I don't have a function that just boom. Okay? That kind of breaks like this. It's more like a piecewise, and you'll get into those more in the future, but for right now, we're dealing with functions that look like this. And it's a polynomial equation where there's one variable involved, okay? If you have more than one variable, you get some interesting looking graphs, but they're not necessarily functions. One famous one, let me see if I can find it. Here we go. Would be this guy right here. Okay, this is the Polynomial of Descartes. I highly encourage you to look this up, okay, and to explore it a little bit. But as you can see, this is a polynomial, but it has two variables, x and y. So we're not necessarily calling it a function, huh? So it's pretty important that we make sure that there's only one variable involved. Okay? All right. Now, let's get back to the examples. Okay? Okay, I think we're good. So here's my first example. And what I'm going to do is identify, is it a polynomial with one variable? And for this first example, it is. There's only z's. The second thing I'm going to do is determine what the degree is of this guy and the leading coefficient. That's what LC stands for. Okay? Now, the degree of a polynomial function with one variable is the one that has the largest integer value. Okay, in this case, it's going to be a 3. The 2 and the 1 here, not the largest, so we don't identify it only by this guy. The leading coefficient that goes with it, which is out in front, is going to be the 7. Okay, so there's our first example done. This polynomial, is it a polynomial with one variable? No. Okay, we have a's, but we also have a b here. Okay, so this is not a polynomial with one variable. I feel like anytime I record, I can't write. I have a hard time writing. Okay? So once again, a polynomial function is continuous. Okay, it doesn't have any breaks, and it has one variable. If we don't have one variable involved, well, we can get some interesting graphs like I showed you with the one, the Polynomial of Descartes. Okay? So we have to make sure we establish that. All right, now we know how to identify a little bit here. And how we can identify is by its degree and leading coefficient. You're probably asking, why is that so important? We'll get to that towards the end. Now let's look at another function where we have to evaluate. Okay, just a little bit of review of that. So looking at this function, this has a purpose. Okay, in my notes, I have a link going to a video. This is the 5-second respiratory cycle that your lungs go through. And this polynomial equation represents it. V is the volume of air in your lungs. T is the number of seconds during that cycle. Okay? So let's say I want to figure out how much volume of air in your lungs are there after 1.5 seconds. Okay? So what I would have to do, first off, is this a polynomial with one variable? It is. What's the degree of this guy going to be? It's going to be 3. That's the highest power. And the leading coefficient would be this guy right here. And that would be what? Negative 37 thousandths. Okay? So just we'll review a little bit. Now, if I'm going to plug 1.5 into here, I have to do that for every variable, right? And this is just a quick review of what we've done in the past. So it would be 1.5 cubed. And then for this guy, it would be 1.5 squared. And then for the last one, it would just be multiplying by 1.5. No powers for that one. Okay? I think so far so good. All right. Now, let's simplify each part. And here it goes. Here we go. I always have my notes out spread so that I can pick up the paper for it, but as you can see, I'm still wrestling for it. So simplifying each part, you would get negative. This would be 1249. This would be 342. And the last one would be 2595. Okay. So as I simplify each one, and just be careful, remember, you do 1.5 cubed, then multiply by the coefficient that's out in front. Adding everything together, we would get that the volume of air would be roughly, if we have to round that, that's a 6 by the way, sorry. If I had to round that, it'd be what, 48 hundredths of a liter? Something very similar to that. Okay. Now this is just a quick little snapshot, right? We're figuring out the volume of air after a certain time period. When you go forward with your math career, let's talk about calculus just for a little bit. What you're going to end up doing is you're going to figure out the total volume that you're getting in your lungs here after from what, 0 to 5 seconds, adding up all those volumes there. Okay, so that's called integration, and that's going to be further along in your math career. But you'll be kind of visiting problems like this again with polynomials and trying to figure out, how can we find the total after those 5 seconds, adding up all those volumes. That makes sense? Okay. All right. So that's the first part. Not too bad, right? Let's talk about the second part, and we're gonna move that whiteboard. Let's do one more evaluation problem. Let's see where I have that, because I just moved my notes around a little bit. Here we go. Okay. Let's do one more evaluation problem. Okay, so evaluate. And this problem is purposely like trying to get you to work with not only a function with a variable, but plugging other variables that are different than what's in this function. So let me explain what this problem's asking. We have a function named b, all right? And that's this guy over here. Here's my function. It has a degree of 2, leading coefficient of 2. It is a polynomial with one variable. And it has the variable m in it right now. Over here, I want to plug these variables, into this guy and simplify. Now, right here, I can see that there's x's. That's okay. I don't have to plug m in. I can plug x's in. I will just take the variable m out and put x in its place. What I'm going to do is I'm going to separate this. I'm going to evaluate this guy first, then this one, and then subtract the result. Okay? Let's go ahead and do that. So here's the first one. I want to plug 2x minus 1 into function b. So anywhere I see an m, I'm going to replace it with a 2x minus 1. Let's go ahead and do that. So 2 times 2x minus 1 squared plus 2x minus 1 minus 1. I think in the last video I made this statement. I like to put parentheses around my substitutions. That way if I go back, I can kind of see what step I'm on. This one you didn't have a choice because you're squaring the entire expression. Okay? Now this, be careful. That's this guy, right? You're multiplying the binomial by itself. There's going to be a middle term. When you multiply this out, I get 4x squared plus 4x plus 1. Okay? I think we're proficient with this now. I can kind of jump right to this guy. All right, and I'm sorry. Apologize. That'd be what? Minus 4x. And then over here, if I simplify this, the parentheses, if they were gone, it doesn't really matter if they're there. This would be plus 2x minus 2. Okay? Let's continue. So it's going to be 2. Oh, sorry. We could just go ahead and multiply this now. 2 times all of this, right? So we get 8x squared minus 8x plus 2 plus 2x minus 2, which comes after. And then for my final result, combine like terms again. The 8x squared, nothing to combine with. Negative 8x, so 2x is a minus 6x. 2 minus 2 is 0. So here is what this guy is evaluated. I'm not done yet, right? I still have to figure out this part. So let's do that next. 3 times b to the x. I'm going to go to my function b. And anywhere I see an m, I'm going to replace it with an x. But I want to do 3 times what I get. So 3 times. Now notice, if I just replace the variable, I'm just getting the same equation. So instead of 2m squared plus m, it's 2x squared plus x. Okay, just like that. Multiply 3 to everything. So 6x squared plus 3x minus a 3. Okay? And this is what this guy is. Now, if I look back up to the original, I'm supposed to subtract these two results. Okay? So boom, boom. Let's go ahead and subtract. So I have 8x squared minus 6x. Subtracting the other guys, which would be 6x squared plus 3x minus 3. 8x squared minus 6x squared is 2. Negative 6x minus a 3x is a 9. And then negative 1, technically, times this guy would be a positive 3. Or if you're subtracting a negative 3, you're still getting the same result there. Okay? And there's my final answer. If I were to evaluate this guy based on this is my function for it, that would be my answer. Okay? Honestly, there's times in mathematics where we have two equations with different variables, okay, depending on what the context of the problem is, and sometimes we want to combine them. This can happen, right? So just kind of preparing you and practicing, okay, I have m's and x's, but can I still keep that straight in my mind? And you can, you definitely can. Okay, all right. So we did one simple evaluation. We did one where there's some variables involved in our evaluation. We discussed how to classify a polynomial function, all right? Now let's talk about the graphs. We're kind of putting everything together now. Let me get to that slide. Go. Okay, so let's take a look at it. And behavior. A lot of information on this graph, okay? If it's an even function, even functions, as you could imagine, are degrees where the powers are even, right? So that would be x squared, x to the fourth, x to the fifth, x to the sixth, and so forth. Their end behaviors are the same, okay? So let's say it is an even function, has an even power, and the leading coefficient is positive. That's telling me, okay, go back to a quadratic. This would be an easy comparison. If the leading coefficient is positive, then it's going to be opening upward. Notice the end behavior. Both the left part and the right part of the function are both facing up. If the leading coefficient is negative, so then it gets reflected and both ends are pointing downward, okay? And this is an x to the fourth function. You might say, wait a minute, these are almost identical. They do behave identically. Now, if I have other things involved with x to the fourth, it's not going to look like this. But the end behaviors will be fine. So what do I mean by that? Well, just a quick for instance. Okay, going back to my goofy graphs here. If I have an x to the fourth, it could look like this. All right? So like x to the fourth plus 3x squared plus 2x minus 1. Okay? I'm not saying this is the graph for it, but just put an example. The other terms will change whatever the middle part's going to give you. But the leading coefficient and the leading term is always going to tell you what direction your left and right part of the function are going to point. Okay? All right. Now, behavior-wise, look at how we describe it. As x values get infinitely larger by a negative, okay, in this direction, my y values increase positively, right? infinitely. Now remember, when you think of infinity, you're not thinking of a number, you're thinking of a behavior. Okay, it's the behavior. It's going increasing positively on forever. Now down here, as my x values go positive, my y values go positive. Okay, so that's what this is describing as the end behavior. Now when it's negative, as you can see, it does change a little bit. My domain and ranges, okay, domains will be all real numbers, but your ranges depend on what? Your y values. For a quadratic, it's your vertex. That would be your minimum or maximum, depending on what it is. Your other even power functions, depending on how it's drawn, it's going to be very similar. Okay, you want to figure out almost like a saddle point. Actually, let me look at this here. So if this is my fourth function, you're looking at like a saddle point here, and you're trying to figure out what would that minimum be for this guy. Or if it's reflected, what would be the maximum? Okay. Now, odd functions, well, that'd be what? 1, 3, 5, etc. Okay. And their behavior is they will point in the opposite directions. Okay. So whether the leading coefficient's positive or the leading coefficient's negative, okay, they're still pointing in opposite directions. That's a characteristic of an odd function or an odd-powered polynomial function. End behaviors, we can describe it the same way. I'm not going to go through each one just for time's sake. We're going to do 2 examples to finish this up. But looking at this guy, as x's are going negative, my y values are going negative infinitely. And then as x values are going positive, my y values are going positive infinitely. Okay? Domain and range would be all real numbers for these guys because, as you can see, I am always going left and right here. Okay? There's really no max or min, unlike the even functions. Okay? Let's do one more thing, and then we'll do 2 examples to wrap this up. The zeros of even and odd degree functions. I like stating it, but I think writing it so you can see it makes it easier. Solutions, roots, zeros. Those words all mean the same thing. Okay? And if we're looking at a function, that's going to be what? The x-intercepts. Okay? That's your solutions, your roots, your zeros. That would make this guy true. Okay? What if it's set equal to 0? So look at what this says. Odd degree functions will always have an odd number of real zeros. Even degree functions will always have an even number of real zeros, or none at all. Okay, let's look at the odd ones first. If it's an odd degree function, if it's an odd degree function, meaning that it's always pointing up and pointing down, right? Either in this direction or the other direction. Notice it can hit the the x-axis once, or it can hit the x-axis a couple times. Okay? So this is 3 times, this is 1. So no matter what, it's always going to be odd. But think of even functions. Okay, this is an even function, and it's hitting it 1, 2, 3, 4 times. But it says none at all, and that's because look at this guy. A parabola we discussed could be above or below. And because the end behavior for the left and right part of the function are behaving the same, unlike the odd ones, the even ones behave the same, so that gives us a possibility of having no answers, no real solutions, or no zeros, or no roots for these guys right here. Does that make sense? Okay. So that's what this is describing right here. Big kind of concept behind it. All right. Okay. So let's wrap this up. Let's look at a couple graphs. Okay. So for this graph, we're going to describe the end behavior, determine if it's odd or even, function, and then state the number of real zeros. Okay? That's what we're going to do. So looking at this guy, I could tell that the end behavior, okay, let me tell you what. I'm going to redraw it on here. It's going to be difficult to go back and forth. Let me just go ahead and... Sorry. There we go. Okay. So it looks like this. Okay. So what's the end behavior telling me? Well, as x goes infinitely positive, okay, this direction, my y values are going to go infinitely negative. Okay, we can see by the graph. It's just going to keep going in this direction here. Okay, and once again, we're describing end behavior. Now look at this guy over here. As x goes infinitely negative, my y values looks like it's going to do the same thing, huh? They're also going to go infinitely negative. Okay. Now I know you're saying f of x. Remember, that's y values. I'm just naming this guy function f. Okay. Now, what would the degree be for this? Well, because both the endpoints are going in the same direction, this is an even degree polynomial. Okay. And then, what are the number of zeros this guy can have? Meaning, what are the number of solutions? This one is going to be ironically, a 0. It's not crossing the x-axis, so there's no solutions for this guy. There's no real solutions, right? We talked about that in the previous lesson. That make sense? Okay, so now let's change this up a little bit. Let's do one more example. Okay, let me change this graph here. And here we go. Okay, so let's say this is my graph. Well, let's describe the end behavior. Okay, so as x goes infinitely positive, my y values are going to go infinitely positive. They're going to agree. And then as my x values go infinitely negative, my y values are going to go infinitely negative. That does not look like an infinity sign, sorry. There we go. Okay, so that's not too bad describing the end behavior. Now, odd or even, I think this is an odd degree function, right? See how the ends are pointing in different directions? So that's a classification of an odd function. And then how many zeros do we have? Looks like just what? We have 1, 0. And that matches the behavior of an odd function, right? Remember, odd functions will have an odd number of zeros for this guy. Okay? And that's it, guys. So a little bit of everything. It's just kind of introducing us to analyzing graphs. And we're going to do a little bit more in the next lesson. One final thing. Going back to this guy over here. Okay. The reason why we're so focused on the degree and the coefficient in front, this right here, okay, determines pretty much the shape of the graph. This is where most of the influence is. So since this is a cubic, okay, we're looking at cubic characteristics, odd number function characteristics for this guy. Okay, the other terms are not going to be as large as this guy, whether it's positive or negatively large, okay, because this has the higher degree. Therefore, this one has more influence, more power over the rest of the terms there, okay? So that's why we spend the first part of this lesson identifying, this right here, because that's going to help us identify the characteristics and what the graph could possibly look like right here, okay? All right, that is it. My notes are online. You can kind of see some other examples, and I highly encourage you to take a look at them. But until next time, guys, this is it. So have a good day, and I will see you all in the next lesson video.